Computers think in ones and zeros, so they represent numbers using the binary number-based system. To find out how this works, keep watching. In this video I'm going to explain the binary numbering system. We'll go through these topics. First, I'll explain the decimal number system. I'm sure you're already familiar with this, but we'll explain it just so that we can go through and see how it compares with the binary system. Then I'll explain the binary system. Again, we'll go back to the decimal system and look at how we do basic arithmetic, and then we'll look at how we can do binary arithmetic. Then towards the end of the video we'll look at negative binary numbers, how we can represent positive and negative values as binary numbers. And finally we'll do a little introduction to hexadecimal, but once you've learnt binary, hexadecimal is really easy. So let's get straight into it. Let's start by quickly looking at how we represent numbers in the decimal system. So in the decimal system it's called decimal because des means 10, and we've got 10 digits to choose from. So we have the digits 0 through to 9. When we write a number in decimal, for example this number here 1, 2, 3, 4, it's 1234. But what it really is a sum of 10 to the power of 0 times 4 plus 10 to the power of 1 times 3 plus 10 to the power of 2 times 2 plus 10 to the power of 3 times 1. So anything to the power of 0 is 1, so that is 4 times 1. 10 to the power of 1 is 10, so that is 3 times 10. 10 to the power of 2 is 100, so 2 times 100, and 10 to the power of 3 is 1000. So 1 times 1000. So we have 1234. That's very simple. It's what we instinctively use all the time, so it's very straightforward. But now let's just have a look at how we count in decimal. So we start off at 0, and then we select the first digit in the least significant column. The least significant column is over to the right, and the most significant column is over to the left. So we take the first digit and put it in the least significant column. We have 1. Then when we want to move up again, we take the next digit, 2, and we keep going through like that. 3, 4, 5, 6, 7, 8, 9. But now we've run out of digits in this column. So what we do is we carry over into this column and select the next digit along for this column, and we reset this column to 0. So after 9 we go to 1, 0, 10. It's very simple. We just carry on like that, going back to the least significant column, adding 1 onto it until we get again 17, 18, 19. We've run out of digits in our set of 10, so we go back to 0 and we go into the next digit in this column to 20. Then we carry on again until obviously we carry on 21, 22, 23 all the way up to 98, 99, and then we've run out of digits for both of these columns, so we carry over into the next column and we set both of these back to 0. 100. So that's how we count in the decimal system. So now let's see how we can count in binary. So with decimal we had 10 different digits to choose from. In binary we have just 2, 0 and 1. And in decimal, in this column we had 10 to the power of 0, 10 to the power of 1, 10 to the power of 2. But because it's binary and we've only got 2 digits, we have 2 to the power of 0, 2 to the power of 1, etc. 2 to the power of 0 is 1, as anything to the power of 0 is 1. 2 to the power of 1 is 2, and then to the power of 2 is 4. And each time we double, so we have 1, 2, 4, 8, 16, 32, etc. When we count, we do the same thing as we do in decimal. So we go from 0 to 1 in the least significant column. And then just like in decimal, we've run out of digits already because we've only got 2 digits to choose from. So we're going to move 1 over into the next column and reset this column to 0. And then we start again by moving up the digits in this column. So we move on to 1. And now, just like in decimal when we got to 99, we've got 1 1 in binary. We need to carry again because we've run out of digits in both of these least significant columns. And we keep counting like this. So after 100, we have 101, 110, 111, and we've run out of digits in all these 3 columns. Carry over into this column, and we keep counting like this. You can see that we get through the columns a lot quicker, but the principle is just the same in decimal as it is in binary. The only difference is we only have 2 digits to choose from. So let's have a look at a binary number. So this number 100 10000. Instead of writing 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, I've actually put in the decimal values. So this is the 1s column, the 2s column, the 4s column. And this number here, we can just add it up. So we've got one lot of 128 and one lot of 16. So this value is 144. So now let's go back to the decimal system and see how we add 2 numbers together. So we're going to add the numbers 125 and 92. So what we do is we start in the least significant column and we add the numbers together. So 5 plus 2 is 5, 6, 7. So we put a 7 down here. Then we move across onto the next column. 2 plus 9 is 11. We put a 1 in this column and we carry 1 over into this column. So 11. Because we've carried this one over, we add this into this column. So 1 plus 1 is 2. 217. Very simple. So now let's try that same sum in binary. So this time, we'll forget about decimal for now. We're going to add these 2 binary numbers together. So we'll start off in the least significant column. We add 1 and 0. That's 1. 0 and 0 is 0. 1 and 1 is 2, but remember we're in the binary system. So 1 and 1 is 0 carry 1. So we write 0 here and carry 1 over into this column. Now we have 1, 1 and 1, which is 3. In binary that is represented by 1, 1. So we put 1 in this column, carry 1 over. Next time we have 1, 1 and 1. Again, that's 1, 1, 3. And then we have 1 and 1 and 0. So that's 0 carry 1. 1, 1 and 1 is 1 carry 1. And then finally 0 and 0, but we've got the 1 carried over, so that's just 1 in that column. So we're adding in binary in exactly the same way as we add in decimal. If we wanted to convert these numbers back to decimal, it's the same sum as before. So we've got, this is 64, 32, 16, 8, 4 and 1. And this is 64, 16, 8, 4. So it's just the same sum as we've done in decimal, done in binary. But if we check the sum, we should find that it's correct. Now let's have a look at how we represent negative numbers in binary. Here's a positive binary number, so we've got 1 times 2 to the power 0 is 1, and 1 times 2 to the power 2, this is 4, so this number is 5. If we want to make this number minus 5, the way we do it in binary is we reverse all the bits first, and this gets us what's known as 1's complement number. So we take all the zeros and turn them to 1's, and we take all the 1's and turn them to zeros. So instead of 0, 0, 0, 0, 0, 1, 0, 1, we're going to change that to 1, 1, 1, 1, 1, 0, 1, 0. This is 1's complement. It's not commonly used, but it's the step towards where we're going. Now, previously, if we look at the positive number, this column was 2 to the power of 7 column. In the negative number, this column represents that a 1 in this column represents that it's a negative number. So we need to know when we have a binary number whether it's a signed binary number, which can be positive or negative, or whether it's just a positive unsigned binary number. So this is our 1's complement value. Now, because if we take 1 and make it minus 1, that makes some sense, but we can't have minus 0, so we would have a wasted number if we had minus 0. So what we do to the 1's complement number is just add 1 onto it. So we take this number and just add 1, so we'll put a 1 here. So this is our 2's complement value for 5. And the reason this is a good way of doing it is that if we continue to count up from minus 5, so we will carry this column here and set these to 0, go to minus 4, we'll then put 1 in here for minus 3, carry over and set that back to 0 for minus 2, and then we'll put 1 there for minus 1. If we now step again, we would carry over into here, but all these would go back to 0, and that would be our next value, 0. So the good thing about 2's complement is it's exactly compatible with positive numbers. So if we subtract 1 from 0, it would almost be like we've got an extra digit here, 1, and if we subtract 1 from it, that would go to 0, and all these would go to 1. So that would be minus 1. So 2's complement. We reverse all the digits, so we switch all the 1's to 0's and all the 0's to 1's, and then we add 1, and that gives us a 2's complement negative representation of a binary number. Now, of course, we've lost one of the digits, so a byte, which is 8 bits. If we have an unsigned byte and we know it's a positive value, it can be any value from 0 to 255. If it's a signed byte, its range is the same, but the numbers go from minus 128 to plus 127. So that's how we represent negative numbers in binary. So finally, we'll have a quick look at hexadecimal. Hex means 6 and decimal is 10, so hexadec means 16. So in hexadecimal, we've got 16 digits to choose from. Now, because we only usually have 10 digits to choose from, we use letters to represent the final 6. So we use these digits here, 0 to 9 and A to F. And this time, the columns represent 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, etc. And when we count, we start off with 1, 2, just like we did in decimal and in binary. We're just moving along our list of digits, 7, 8, 9, and then A, which is, if it was decimal it would be 10, but it's A in hexadecimal, then B, then C, D, E, F. Now, so this is decimal 15, but hexadecimal F. Now we've run out of digits, so we're going to carry into this column and move that column into the next digit and put this column back to 0. So the next value is 10. Notice I'm not saying 10 because it's not 10, it's 16, but the digits are 1, 0. Now, why do programmers like hexadecimal so much? Let's say we've got a binary number like this one and we want to write it down. It could be very confusing and also very long-winded to write down this number 0, 0, 0, 1, 1, 1, 1. You can see how it can be easy to make mistakes and very confusing to look at that. But because 16 is 2 to the power of 4, what we can do is we can split these digits into groups of 4. And then if we put our hexadecimal table back in, we can take these groups of 4 and look at them individually as a set of 4. So 0, 0, 0, 1 is 1 in decimal, also 1 in hexadecimal, so let's put a 1 in there. 1, 1, 1, 1, that would be 1 plus 2 plus 4 plus 8, so that's 8, 9, 10, 11, 12, 13, 14, 15, or maybe more appropriately I should say 8, 9, A, B, C, D, E, F, so that's an F in there. This is 0 lots of 8, 0 lots of 4, 1 lot of 2, 0 lots of 1, so that's a 2 in there. And this would be 8, 0 lots of 4, 9A, 0 lots of 1, A. So you can see that hexadecimal and binary is much more interchangeable. If we wanted to split this, turn this back into binary, we'd look at 1, 0, 0, 0, 1, F would be this, 2 would be that. So you can see that binary and hexadecimal are easily interchangeable. It's much more convenient to use hexadecimal if you're converting to binary. So that wraps up our lesson on the binary number base system. If you've learned something from this video, give it a like. This video is actually part of a series where I'm showing how computers work from the ground up by simulating and animating a model of a CPU to show you how all the different parts of the computer work. If you'd like to watch a series, then subscribe to my channel so you can see the videos as I make them. Thanks for watching.